Hello and welcome to our unit on oceans and water. We're going to learn about waves, tsunamis, and all those kind of interesting things that have to do with water, the depths of the ocean, all those kind of things are going to be in this unit. So let's get started. Section 1 is the properties of water. How would you describe to someone who had never seen it before? You might say that pure water has no color, no taste, and no odor. You might even say that water is a rather plain, ordinary substance. But if you ask a chemist to describe water, the chemist would say that water is very unusual. Its properties differ from those of most of the familiar substances. The structure of water. Could you and the chemist possibly be talking about the same substance? To understand the chemist's description of water, you need to know something about water's chemical structure. Like all matter, water is made up of atoms, just as the 26 letters of the alphabet combine in different ways to form all the words in the English language. About 100 types of atoms combine in different ways to form all types of matter. Atoms attach together or bond to form molecules. Two hydrogen atoms bond to an oxygen atom, form a water molecule. A short way of writing this is to use the chemical formula for water, H2O. Figure 1. Let's look at figure 1. Figure 1 here shows how the hydrogen and oxygen atoms are arranged in a water molecule. Each end of the molecule has a slightly electric charge. The oxygen end is a slightly negative charge. The hydrogen end has a slightly positive charge. A molecule that has electrically charged areas is called a polar molecule. Because water consists of polar water molecules, it is called a polar substance. Have you ever played with magnetic bars? If so, then you know that the opposite poles of two magnetics attract each other. The same is true with the polar molecules, except that an electric force rather than a magnetic force causes the attractions. The positive hydrogen end of one water molecule attracts the negative oxygen ends of nearby water molecules. As a result, the water molecules tend to stick together. Okay, this is a hydrogen atom. We have one hydrogen and two hydrogen atoms, and they have a slightly positive charge, and the oxygen atom here in the center has a slightly negative charge. Water molecules attract each other. So there's a small attraction between all the water molecules. All right. So this attraction among these water molecules is responsible for water's unusual properties. So in the capillary action, you notice that water kind of climbs up the tube in a straw. That's called capillary action. Okay, key properties of water. Many of water's unusual properties occur because of the attractions among the polar water molecules. The properties of water include capillary action, surface tension, the ability to dissolve many substances, and high specific heat. So capillary action. Just as water molecules stick to one another, they can also stick to the sides of a tube, such as a straw. The next time you see a drink with a straw, look closely at the level of the liquid outside and inside the straw. You will see that the liquid rises higher inside the straw. As water molecules are attracted to the straw, they pull other water molecules up with them. Similarly, water will climb up into the pores of a brick or a piece of wood. The combined force of attraction among water molecules and the molecules of surrounding material is called capillary action. Capillary action allows water to move through the materials with pores inside. Capillary action also causes water molecules to cling to the fibers of materials like paper and cloth. You may have seen outdoor athletic clothing that claim to wick moisture away from your skin. Capillary action is among the cloth fibers pulls water away from your skin. Pulling the water away from your skin, the fibers keep you dry. Surface tension is the tightness of the water surface. It keeps a water strider from sinking. You can see that over here in the picture. Surface tension. Have you ever watched water striders skate across the surface of a pond without sinking? They are supported by the surface tension of the water. Surface tension is the tightness across the surface of water that is caused by polar molecules pulling on one another. The molecules at the surface are being pulled by the molecules next to them and below them. The pulling forces the surface of the water into a curved shape. Surface tension also causes raindrops to form round beads when they fall onto a car windshield. Universal solvents. Many substances dissolve in water. Have you ever noticed that sugar or salt will dissolve in the water? Well, that's why it's a universal solvent. What happens when you make a fruit drink from a powdered mix and stir the powder into the water? The powder seems to disappear. When you make the fruit drink, you are making a solution. A solution is a mixture that forms when one substance dissolves another. The substance that does the dissolving is called the solvent. In this mixture, the water is the solvent. So these are some good scientific terms you need to understand. Solution and solvent. So solution is the one substance that dissolves another, and the solvent is what is being dissolved, okay? I'm sorry. Solvent is doing the dissolving. Right. Many substances dissolve in water because water is polar. The charged ends of the water molecule attract the molecules of other polar substances. Water dissolves so many substances that it is called the universal solvent. It can dissolve solids such as sugars and liquids such as bleach. Water can also dissolve many gases, including oxygen and carbon dioxide. Substances that have molecules with no charged regions are called nonpolar substances. Nonpolar substances do not dissolve well in water. Okay? Specific heat. It is a steamy summer day. The air is hot, the sidewalk is hot, and the sandy beach is hot. But when you jump into the ocean, the water is surprisingly cool. If you go for an evening swim, however, the water is warmer than the cool air. You feel the difference in temperature because of water's unusually high specific heat. Again, this is another term you need to know. Specific heat is the amount of heat needed to increase the temperature of a certain mass of substance by 1 degree C. Compared to other substances, water requires a lot of heat to increase its temperature. Water's high specific heat is due to the strong attraction among water molecules. Other substances, such as air and rocks, have weaker attractions between their molecules. The temperature of these substances rise more quickly than that of water that is heating the same amount. One effect of water's high specific temperature is that land areas located near large bodies of water experience less dramatic temperature changes than areas far inland. In summer, the sun's heat warms the land more quickly than water. The warm land heats the air above it to a higher temperature than the air over the ocean. As a result, the air is warmer inland than on the coast. The opposite effects occur in winter. Land loses heat more quickly than water, so the air above the land is cooler. Okay, so why does water have a high specific heat? We talked about that because it has a high attraction between the water molecules and is polar. Okay. All right, changing states. Going with changing state. It's a hot, humid summer. To cool down, you put some ice cubes in a glass and add cold water. You are interacting with water in 3 different states or forms: solid, liquid, and gas. The ice is solid water. The familiar form of water is a liquid, and the water vapor in the air is gas. Water is the only substance on Earth that commonly exists in all these different states. Figure 4 shows how the arrangement of water molecules are in different states. So you can look at them in solid, liquid, they're closer together. And see the little bond in between the solids, where liquid is kind of moving around and vibrating, and gas they're further away. Boiling and evaporation. If you have ever poured water into a pot, you've seen how the liquid takes the shape of the container. This is true because the molecules in the liquid water move freely, bouncing off one another. What happens if you place the water pot on the stove and heat it? As more energy is added to the liquid water, the speed of the molecules increases and the temperature rises. At 100 degrees C, the water boils and and a change of state occurs. The molecules have enough energy to escape the liquid and become invisible water vapor. The molecules in a gas move even more freely than those in a liquid. Another way that liquid water can become a gas is through evaporation. Evaporation is a process by which molecules at the surface of a liquid absorb enough energy to change the gaseous state. If you let your hair air dry after going swimming, you take advantage of the evaporation. Condensation. Condensation. As water vapor cools down, it releases some of its energy to the surroundings. The molecules slow down and the temperature decreases. As the temperature of the gas reaches 100 degrees C, the water vapor begins to change back to the liquid state. The process by which a gas changes to a liquid is called condensation. When you fog up a window by breathing on it, you are seeing the effects of condensation. The invisible water vapor in your breath is cooled by the window and forms drops of liquid water. Freezing. If those drops of liquid water cooled, the molecule would lose energy. They would start to move more and more slowly. At 0 degrees C, the liquid water freezes, changing into solid ice. If you have ever observed an icicle forming from water dropping off a roof, you have seen this change of state in progress. Melting. Suppose that you put an ice cube in a pot and place it on the stove. As you heat it, the molecules in the ice would start moving faster. The temperature would rise. When the temperature reached 0 degrees Celsius, the solid ice would melt and become liquid water. So what is condensation? The condensation is what occurs on the outside of your water glass. So the air outside is starting to cool down and the molecule is starting to get colder and it forms back into liquid from water vapor. So you can see as liquid gets hotter, as water gets hotter, it goes through evaporation and becomes a gas. You can see how far the molecules are apart. When it gets colder, the water molecules start getting closer together and form liquid. Again, liquid, if they're still moving and vibrating. Freezing, you can see that these little bonds are forming, and melting again, they're starting to move quicker again. Okay, this is the end of section 1 of this unit, water properties. So you'll be doing section 1 assessment. So check out IC and submit your homework. Thanks. Bye.